Hi everyone, here we are for the last practice problem in chapter 5. It's number 3. I'll go ahead and read it. A New York City subway arrives every 8 minutes during rush hour. The length of time a commuter must wait from the moment they step onto the subway platform is uniformly distributed. And in part A, we're supposed to graph the probability distribution. I actually have the graph up there already. Um, you can see that. So the idea is if a subway arrives every 8 minutes, then if a commuter steps onto the platform, it's possible that they then just immediately get onto the subway that's pulling up, in which case they've waited 0 minutes. It's also possible that the moment they step onto that platform, the train is pulling out of the station and they're going to have to wait a full 8 minutes until the next one comes. But probably, most likely, it's going to be somewhere in the middle. They're going to have to wait somewhere between 0 and 8 minutes. Again, this is a continuous random variable. Um, we can be as accurate as we like with the decimal places on how many minutes they are waiting. So there's the graph. It's going to be somewhere between 0 and 8, and then we make a rectangle out of it, and that's all we need to do. Don't worry about indicating how high up it is. It turns out that's what we're going to look at in Part B. Part B says, what is the probability density function f of x? So we did not do one of these in the last practice problem because they don't come up nearly as much as the probability questions. But let's do one now. For the uniform distribution, f of x equals 1 over b minus a. Well, in this case, what are the a and the b? Of course, the a is always the lower, the b the upper. So we'll plug those in, 1 over 8 minus 0. So in this case, f of x, if we simplify, just 1/8. And it turns out that if you wanted to know is how tall this rectangle is, 1/8. If I could say anything more about that, think what's the area of that the full area of that rectangle? Well, 1/8 times 8, that area would be 1, which represents 100% of the data. That I think that was mentioned back at the very beginning of the lecture, that the area underneath your f of x is always equal to exactly 1 when you add all of it together. So when we take little bits of area, that's always something smaller than 1. That's a probability. Okay. If you read that, this is probably not new to you, but it's good to hear it again. Let's get to something more interesting. Part C, it says, what is the mean wait time? What is the average wait time for somebody waiting for the next train? So, or subway. So we have a formula for that. It's a plus b over 2. Turns out if we take the average of a and b, that'll be the average wait time. For a uniform distribution, that makes sense. Just find the middle of a and b. And of course, in this case, if we take 0 plus 8 divided by 2, that's 4 minutes. The average person, or we would expect, if we were a commuter, we'd probably expect, I know one arrives every 8 minutes, so on average, I'm going to wait 4 minutes, on any given day. Some right there in the middle. Luckily, we have that formula as well, a plus b over 2. What is the standard deviation? Now, this one is not something we can just look at and tell. We've got this formula. I'm not going to explain where that formula comes from. I'm just going to tell you that that's what it is. The square root of the quantity b minus a squared over 12. So luckily, if we know that formula, we can, again, plug in our a and our b. This case, 8 minus 0. And I'm just going to jump to the answer here. I invite you to do these along with me. In your calculator, sigma is 2.309 in this case. Okay, so we've done quite a bit already. We've graphed it, did f of x, mean, standard deviation. Now we're going to get to the probabilities. Okay, so part E says, what's the probability that a commuter waits less than 1 minute? And now this one is really straightforward. I won't repeat the formula. Capital X less than 1, somebody's waiting less than 1 minute. Well, we plug in our x minus a. There's b minus a. 1 minus 0 over 8 minus 0. And we simplify that. Of course, that's 1/8, and we get the decimal 0.125. The chances somebody waits less than a minute. They got a 1 out of 8 chance. Makes sense for uniform distribution. Okay, how about F? And I'm kind of giving it away a little bit here, but no big deal. What is the probability a commuter waits somewhere between 5 and 7 minutes? So their wait time is somewhere between 5 and 7. We don't have a formula for something like that, so we need to think of it as the probability that x is less than 7, and then we'll subtract the probability that x is less than 5, all of the area up to 7, subtract all of the area up to 5. What's left is just the little bit of area between 5 and 7. That's what we want. So if we apply our formula to each of these, right, 7 minus 0, 8 minus 0, 5 minus 0, okay. If we do each of those separately, 7 over 8, 5 over 8. Sorry, it's getting a little bit blurry. Let me pull it up. Our final answer happens to be 0.250. They've got a 25% chance that they'll have to wait somewhere between 5 and 7 minutes. Okay, so hopefully we're kind of picking up the pattern. If they're ever asking for the value to be between two values, always follow this style. Start with the bigger one, subtract, and then the lesser one, it's the area. That'll give you just the area between those numbers. Okay, we got one last question, and it's about, it doesn't say the word, but it's a percentile question. They say, part G, 70% of commuters wait more than how long for the next subway? Now this one is a little bit harder, it's a little bit trickier than the other percentile questions that we've done. For one, they don't say the word percentile. There's actually a reason they don't, because they're phrasing this as 70% of commuters wait more than how long. A percentile always indicates a less than. But here they're saying it the other way around. They're saying, what are the chances that capital X is more than, is greater than little x? What value of little x would cause that probability to be 0.7? 70% of commuters wait more than how long? Capital X is more than what would give me 0.7? And there's my, they say more than in the question. So we need a greater than or a more than when we write our probability. Okay, we had a question like this back with the average hours of, or how long it took people to fall asleep at night. If this is ever a greater than, then we need to use the complement. We need to think of that as 1 minus the less than. If we think of the less than and we take that away from 1, that's saying the same thing. If that's not clear, maybe go back to that video, look at that that first part 1 of practice problem number 1 again. There was a similar question where we turned a more than into a 1 minus less than. So this is what equals 0.7. Now I know a formula there. I could go ahead and put that formula in and that would be fine. I'd actually rather do this a little bit simpler. Hey, if 1 minus this is 0.7, wouldn't this equal 0.3? I could think of it that way. That's a little bit easier. 1 minus something is 0.7. Well, that something just equals 0.3. Okay, I'm probably over-explaining for a lot of you guys. I mean, you might even feel comfortable jumping from this statement straight to that statement. You know, a greater than, hey, turn it around. That means I need the complement there. 0.7 turns into 0.3. Okay, at that point, I'm going to use my formula. I don't know x, but I do know a and b, and it's equal to this. I'm going to solve for x. Now, what's great is nothing tricky here. Pretty straightforward. X over 8 equals 0.3. I ran out of page, so I'll continue that. Well, there's my answer. Multiplied by 8, x equals 2.4, and the units happen to be minutes. 70%, I've got the written explanation, 70% of commuters will end up waiting more than 2.4 minutes. That's a reasonable answer. If the average person waits 4 minutes, right, most people are going to have to wait more than 2.4 minutes for sure. 70% seems about right. Not a bad idea on a lot of these is even to kind of give yourself a graph, make sense of it. If we were in class, I'd be doing this for like every one of these questions, honestly. You know, if there's our 0 to 8, hey, 2.4 is about right there. Does it make sense that 70% of commuters are going to have to wait more than that? Yeah, that's probably 70. That's 70% of the total area. All right. I should have done it back here with the between 5 and 7. You know, if we draw that, 0 to 8, give yourself a sketch. You know, that's 4 there in the middle, so maybe 5 is here, 7 is here. What are the chances that any random person falls somewhere between 5 and 7? And that's exactly 1/4 of the total area. So maybe that clarifies things a little bit. Well, that is the end of chapter 5. I will see you guys in our live session, hopefully on Tuesday. Come with questions, and you know, we'll take care of any concerns then.